Dr. APJ Abdul Kalam, man needs its difficulties because they are necessary to enjoy success. All of us do not have equal talent, but all of us have an equal opportunity to develop our talents. With this quote, I, Harish P., Assistant Professor, Department of Mechanical Engineering, Vrindavan Group of Institution, Bengaluru, take this privilege to welcome you all to this wonderful webinar on smart materials and structures organized by the Department of Mechanical Engineering, Vrindavan Group of Institution. Firstly, I would like to welcome our beloved Chairman, Padma Shri Dr. B.R. Shetty sir, in his absentia, who gave continuous support and encouragement in conducting knowledge-seeking sessions. Now, I would like to welcome Dr. Rajashekar Patil, Principal and Dean, Research and Development, Vrindavan Group of Institution, for giving us this opportunity to organize this program. We welcome you, sir. Now, I would like to welcome our resource persons of today's webinar, Dr. Syed Basith Muzammil, Director, Research and Consultation, Exposes Data Labs and Material Tech Consulting, Bengaluru, making his time free for us and accepting invitation to deliver his knowledge. We cordially welcome you, sir. I would like to welcome Dr. Sumud Daniel, HOD, Department of Mechanical Engineering, Vrindavan Group of Institution, one who stands always with us in conducting this program. We welcome you, sir.
Thank you.
Also, I would like to welcome all the coordinators, HODs of various departments, and staffs of mechanical departments and other departments, and all participants to this wonderful webinar. Now, I would like to request Professor Azim Pasha, sir, Assistant Professor, Department of Mechanical Engineering, Vrindavan Group of Institution, to introduce our resource persons for today's webinar. So over to you, sir.
Good afternoon, all of you. I, Azim Pasha, Assistant Professor, Department of Mechanical Engineering, Vrindavan College of Engineering, welcome you all for this webinar. It gives me immense pleasure to introduce today's resource person, Dr. Syed Basith Muzammil, for this webinar. He obtained his B degree from Gosha College of Engineering and ME degree from UVC Bangalore University and PhD from UVC Bangalore University. He served as a project scientist in CSIR National Aerospace Laboratories for 2 years, and he worked as an assistant professor in HKBK College of Engineering for 3 years, and worked as an assistant professor and member of Research and Technology Transfer Council, Dair Dawa University, Ethiopia. Now he is the current director of Research and Consultancy, Exposes Data Labs and Materials Tech Consultancy, Bangalore. He is having 2 patents on his name, and he has published several national and international journals in reputed journals. I welcome Dr. Syed Basith Muzammil for this webinar, sir. Thank you, sir.
Thank you so much for the kind addressing of the introduction. So,
thank you, sir. Thank you for your introduction, sir. Now, I request Dr. Sumud Daniel, HOD, Department of Mechanical Engineering, to address this session.
Thank you, Arisha. Good afternoon, one and all. First, I take this opportunity to pray for our departed or beloved Naima Master. Let his soul rest in peace. And also our fraternities working in various colleges who have left us due to the COVID-19, and also our student fraternity who are studying in different colleges who are lost due to the COVID-19. I pray God to let their soul rest in peace. I thank our beloved chairman, V.R. Shetty sir, for his unflinching support to organize the webinar. I thank our respected principal, Dr. Rajashekar Patil, for his moral support and assistance to organize the webinar. I thank and welcome our eminent speaker, Syed Basith Muzammil sir. I welcome all respected HODs and dear faculties of various departments to this webinar. Today's topic, smart materials and structures. For this session, I welcome all my dear students to this webinar. Today's session on smart materials and structures enlightens us wide applications of smart materials in Industry 4. Once again, I thank and welcome all the participants, eminent speakers, and respected HODs of various departments. And now I hand over the session to our eminent speaker, our Syed Basith Muzammil sir. Over to you, sir.
Yeah, thank you, sir. Thanks for your beautiful words and a warm welcome. So, shall we commence the session?
Yes, sir. Yes, you can proceed, sir.
So, I welcome to all the participants, dear students, colleagues, research scholars, and aspirants. So, this session is majorly concerned with the technology, which is partially into the application and more into the research arena. So we have to understand what these smart materials are, why these materials are called smart, and what makes these class of materials to stand aside the conventional sort materials, conventional category of materials. So it is of the polymer-based, metallic-based, or ceramic-based, or in kind of like hybridized materials or composites. So today, we are going to focus more onto the functional concepts of the smart materials. I'm going to just enlighten onto the materials, its classifications, its understandings, like how exactly the material behaves in different interaction, influence of the different physical stimuli, and why these materials are called as smart materials and its significance. Second part is we need to understand the applicability of this. So post understanding the characteristics, behavior of these materials, we have to see the potential applications. So after understanding these applications, we have to go for the research opportunities and trends and investigation gaps in smart materials and structures. Where can it be deployed? How we can make the systems, structures, devices to be more functional, more applicable, and it will be like more utilizable into a different classes of industrial applications. Then we'll go for the advanced characterization techniques, how we can just differentiate in the form of materials. So first we have to understand the material, its fundamental, the science behind these materials, and the interaction of these materials with the other class of materials, its deployment and its applicability. So we have to understand in that way. So characterization is very much important to define the behavior of that particular materials. Next, a trend in research, and that's what how the investigations can be taken up for the better utilization and functionality of the materials. I hope this screen is visible, right? It's operational, isn't it?
Yes, sir. Yes, sir. Visible,
Yeah.
sir.
Yeah, thank you. So let's see. First, we have to understand how we can just define the smart materials. So smart materials, in its definition, are the new class of materials that dramatically being influenced by the physical stimulus. May that physical stimulus be electrical current, may that be chemical influence, may that be a mechanical pressure, mechanical stresses, or may that be a temperature influence, agitation of the thermal forces, thermal loads, or may that be a pH, that's what the chemical influences, or the moisture, or the magnetism, or the light. So that means these physical stimuli, these physical agitations of the different forms of energy, whether it is a mechanical forces, touch, temperature, electricity, or whatever it is. So different materials are being designed to influence onto different physical stimulus. So that's what we have to understand, how these are utilizable and how these are functional. So these class of materials can be better used for sensing a change in physical stimuli. Let's take an example. You'll be having a dial gauge. The mechanical engineers can easily understand a dial gauge. So how we can use that? We can use a difference in heights or difference in sizes. We can easily understand that. With the touch of that, or with the plunge, small plunge, we can understand. So that's a very, very small mechanically operated gauge. So that can be easily understood. Now, what happens when temperature changes? So we'll be having thermometers, we'll be having thermocouples. So that is also going to change its characteristics. So that change in characteristic generates electrical pulses. So that means under the influence of temperature change, under the influence of agitated temperature, it's going to be a change in EMF. So that is how that can be taken as the input in judging the temperature. So that's what the thermocouple is basically working. So like that, we'll be having electricity, pressure, and moisture, pH, like we'll be having pH papers and all. So all these things are going to be worked. So that means like we have to understand how this is going to be worked as a sensor. So this can easily be worked as a sensor, and then these materials can be used to actuate a mechanism. Let's take an example. I think everyone knows about the piezoelectric sensors, piezoelectric transducer, piezoelectric materials, the quartz crystal. So everyone are aware of this. So that is what, like under the influence of electrical pulses, these materials are going to change its size. So that's what it expands and contracts. So this change in strain or the deformation, what is going to be affected under the influence of electrical current or vice versa. That means if it is going to be like pressurized or deformed, then it is going to discharge an electrical pulse. So this class of materials, that is what the PZT or piezoelectric materials are going to be acting as the actuators. So likewise, we'll be having shape memory alloys. So we will come to the shape memory alloys in the next few minutes. So that's what, like a better example is like how to actuate a mechanism without any linkages, without any kind of like electrical influences. We are going to actuate this thing. So that's why these materials are going to act as an actuator. That's it. To control the devices or structures, with the use of these class of materials, we can better control the devices, structures. May that be for the solenoid thing, may that be for the fuel injectors, may that be for the ultrasonic, ultrasonic cleaning and the motors of the piezoelectric motors and all. So we can have a better control over any kind of mechanisms and the devices and structures with the embedment of these types of materials. Damage detection and monitoring, especially structural health monitoring. We can use the fiber optics. We can use the conductive polymers. We can use the shape memory polymers, shape memory alloys. So these things are being used in modern aircraft structures to heal and to monitor online structural health. So that means like when that aircraft is flying in the space, then if there is any kind of structural damage, because aircraft structures are maximum 90 to 100% structure is made up of the composites. So always you can say at least 70% is made up of the polymer composites or FRP composites. So these fibrous materials, there may be the delamination, there may be some kind of, due to turbulence, there may be a crack, there may be a delamination, there may be a kind of like a crack generation, and then it propagates. If we have the shape memory alloy wires which are to be embedded into it, then certainly it detects the crack, and then the signals can be easily transmitted to the master computer, and from there may be a kind of a crack closure mechanism could be taken up. So that can avoid the catastrophic failures or accidents. So that is how the online structural health monitoring and structural health healing can be achieved with the help of this materials. That is self-correcting and self-control and self-healing. That's what. optimum and effective shock absorption and damage arrest. So let's take for the shock absorption. We will be having shock absorbers. Now we can say if a truck's dampers or shock absorbers are designed for 10 metric ton of load carrying capacity. Let's say the truck is designed for carrying 10 metric ton. Now, these shock absorbers will be very much effective only at the 10 metric ton of load. When it is unloaded, when it is not having, after loading, when it has to return, then it will be empty. It creates a lot of vibrations in the structure, in the truck and all. So there, this suspension will not be more effective. So now, with the help of the rheological fluids, electrorheological fluids, and magnetorheological fluids, suspensions can be designed. The dampers can be designed to more effectiveness, so that we can say it can offer the optimum cushioning effect, optimum vibration absorption effect, whether it is fully loaded, that is to a 10 metric ton, or whether it is no loaded, or whatever the basic load we have. So that is what the next, the very biggest achievement we have achieved through these smart materials. So now, generally listed smart materials. So we have piezoelectric material, shape memory alloys or shape memory polymers, magnetorheological and electrorheological fluids, magnetostrictive and electrostrictive materials, pH-sensitive polymers, chromogenic systems like halochromic materials which change onto the color, thermochromic materials that change the color under the influence of temperature, and electrochromic materials that change color under the influence of the electrical conduction. So that's how the materials are generally listed. We have listed over here, and we will have it just onto the fundamental concepts. So I think most of you knows about this piezoelectric material. I need not to stress more onto this piezoelectric material. These materials are generally naturally characterized. So we will be having so many naturally available piezoelectric materials also, and we are going to develop, or we are going to hybridize the materials for the better piezoelectric effect. So piezoelectric is basically means like under the influence of these materials, are under the influence of the mechanical pressure, mechanical strain, or mechanical deformation, it generates electrical pulses. So that means electrical current can be generated over there that can be used for sensing. I mean, of course, it's not like into so many volts or so many kilovolts. No, it's not into that. So some millivolts or microvolts will be generated, no problem. That can be used as a signal to understand like how much of stresses, how much of mechanical loading could be done. So we'll be having so many other applications for this piezoelectric materials and piezoelectric transducers. Similarly, on the vice versa, on contrary, what it happens is when you are going to agitate this material or transducer with electrical pulses, then it expands, and when you remove, it contracts. So that means like it expands and contracts. There may be a mechanical change or mechanical deformation could be seen under the influence of the electrical agitation. So now we can clearly understand how this picture shows like how exactly this expands and contracts under the influence of electrical current, or it generates electrical pulses under the influence of mechanical strain or mechanical loading. So that's how we can see the applied pressure. Now we can see here applied pressure or the vibration. Based on that vibration, based on the intensity, based on the load, it generates the amount of electrical current over here. So that's what the magnitude we can easily observe here. Similarly, when you are going to give electrical current, then certainly what happens here, it expands and contracts. Now, this clearly shows how this electrical current can be seen. Now we can see in this animation, you can clearly understand how this works. Of course, it may not be into the considerable amount of deformation, but of course, so we are the naturally available piezoelectric materials are not going to offer a very high or very good piezoelectric effect, but certainly we are developing nowadays materials with PZT and PBT, that is lead, zirconate, and titanate. So we'll be having so many other combinations of the piezoelectrics. So we are developing for the better piezoelectric effect and high amplitude of the vibrations that can be achieved. Another example is another one more important aspects of this piezoelectric is this can generate or this can achieve ultrasonic frequency. That means the expansion and contraction can be achieved to the ultrasonic frequency. That is 20,000 times it can expand and contract. So that means that can be achieved only in the three possibilities. One is Galton's whistle. So Galton's whistle is like it was detected in it was discovered in early 19th century. So that can achieve the the vibration of the membrane. Vibration of the membrane can be of the range of ultrasonic frequency. That is a Galton's whistle. Second is piezoelectricity. So this piezoelectricity can be achieved like when you are giving at a high frequency current, then certainly what happens is it can generate the expansion and contraction. That means the expansion and contraction can be of the range of the ultrasonic frequency. So in a single second, it can achieve 20,000 and more than 20,000 times of expansion and contraction. So that can be used in various applications. This effect can be used in various applications. That is engine knocking sensors, pressure sensors, diesel fuel injectors, and ultrasonic motors, piezoelectric motors, ultrasonic cleaning. So all this, and you can say ultrasonic dispersion equipments we're using in that way. So that means like for dispersion of a different different materials into a liquid for homogenization. So we are going to use this ultrasonic dispersion equipment. But there also we are going to use this piezoelectric transducer so that it can achieve the vibrations of the range of ultrasonic frequency. That's 20,000 parts and all. And third is the magnetostriction, the principle of magnetostriction. That is also with the help of the electrical influence, electrical current, it can expand and contract. The soft ferromagnetic core can be used over there under the that is surrounded by the high voltage windings. So when the high voltage current is being given, then it expands, and that soft iron core is again being contracted when it is being taken off. So that's what it can be achieved. This ultrasonic frequency, that is the expansion and contraction rate, can be achieved in magnetostriction as well. So this is the basics about the piezoelectric materials. So now various applications, as I have told. So in the cigar, the lighter can be used, and you'll be having so many other applications like diesel fuel injector. They're using, and of course the spark plug we're using there, pressure sensors, engine knocking sensors, and ultrasonic piezoelectric motors and all. So they are the potential applications of piezoelectric materials. Now shape memory alloys. What this shape memory alloys? Most of the people are aware of this shape memory alloys. What this shape memory and alloy? So these are the alloys. These are the alloys. First, these shape memory alloys are discovered in the ordnance industry. So that's what nickel and titanium based alloys. This nickel and titanium is combined together almost to a range of 50:50 by volume, and with the some copper and some nickel addition, that is 1 or 0.5% or so. That's of negligible. So these alloys are made, and these alloys are characterized and studied, nickel and titanium based alloys, and they could understand, they could find that these alloys have got the tendency to memorize its shape, to understand, to keep its shape a common, constant shape. So then the further investigations has been taken up, and these alloys are commonly being known with nitinol alloys. So that is what nickel titanium novel ordnance alloys. So that's what it is being known as. So now these shape memory alloys are the alloys, that's what generally I'm telling, the thermal based shape memory alloys, that is nickel and titanium based alloys, which are being used with some other forms of material. That's what intermetallic elements are added onto that to achieve different characteristics, that is to memorize the shape under the influence of thermal agitation. So usually we have the two types of shape memory alloys. One is the regular thermally agitated shape memory alloys. Second is magnetic shape memory alloys, MSMA. SMA and MSMA. SMA is thermally agitated shape memory alloys, which are going to memorize, which are going to remember the shape and size of the structure under the influence of thermal agitation. Now, these alloys are pseudo-elastic sometimes, and sometimes they are super elastic in nature. What is this pseudo-elastic? So that means these are not elastic. This is the plastic deformation. Now, everyone, all mechanical engineers knows that. So following the elasticity modulus, after the elastic limit, it undergoes the plastic deformation. So now we can say the elastic deformation is very minute. Sometimes it is not visible. It cannot be seen by the naked eyes. So that's what for the materials, metallic materials, we cannot see the elastic range. So that is deformation under the elastic limit. We can see deformation in the plastic limit. That means if we are going to bend this, then certainly it is going to bend permanently. It cannot come back. So once the load is being removed, it cannot come back to its origin position. Now, I am touching this. I'm touching on this. Then you can say it is getting deformed. Certainly, it has got some weight. And when I'm touching, this is going to get deformed. In the micro level, in the nano level, it is going to get deformed. And when I'm leaving this, it has come back. So that means when we are seeing from the high-end microscopes, then we can understand that we can see that it has got small deformation, and after the removal of the load, it has come back to its original position. So that is the elastic deformation. Plastic deformation is like we are bending something, then if you are leaving, if you are bending a rod, then it is bent. Though if you are removing load also, it's not coming back to its original shape. So that's the plastic deformation. But in this shape memory alloys, when you are deforming, it is deformed. And then under the influence of thermal agitation, thermal load, that is when it is heated back, then it comes back to its normal position. So that means it can reach to its original position, though after it is plastically deformed. So that is what, though it is only the bending, or it may be into other form, other shape. So it memorizes that shape and it comes back to original shape. So that means it can memorize at least 2 shapes. So this is the shape memory alloys. I think everyone has understood what this shape memory alloys are, why these are called as shape memory. So alloys such as nickel titanium, copper aluminum nickel, ferrous magnesium and silicon. So like that, you'll be having some combinations of alloys which are going to offer the shape memory effect into it. So major applications are craft applications. So you'll be having so many robotic applications and dental braces, the braces used for arrangement of the teeth. So that is the dental implantations, and stents in the heart. Stent. Everyone might have heard of the stent. There's something, some metallic element which is going to use in angioplasty. And when there is a blockages in the vessels, then certainly it goes and makes a passage for the blood to flow in. So that is the stents. So stent is also a shape memory alloy material. So that is going to expand and permanently deform it. And that makes the passage of the blood to flow into the so that's what the applications of this. So to better understand how this shape memory alloys and shape memory effect is, we have to understand these things. So it makes, when I'm coming to explain more onto this shape memory effect. So this, in technical terms, the people who are from the material science backgrounds and who have understood more into material sciences, then they will understand what this martensitic and austenitic state is. Now, let's take an example of this ferrous-based material in forging and all, right? So we are going to make it to a recrystallization temperature. That is the austenitic state. We are going to heat the iron to a red hot condition. Then we are going to hammer. Why we are doing that? Because that is the recrystallization temperature. That means the atoms can easily rearrange. Atoms can easily migrate from one place to other place. So that's how we can reshape the metallic elements from there. So that is the austenitic state. Martensitic state is the lower temperature state. So we have to understand first thing, that is martensitic state is the low temperature state. Austenitic state is the high temperature state. So that means the deformation state is austenitic state. Now the 2 stages here, the stresses graph can be seen here. So in this, the temperature change can be seen over here. So that means when the material is being taken, when a wire is taken, that is made up of the nickel and titanium, that is shape memory wire is taken and it is being deformed. Now we have to understand what is its what to say, the original shape, or you can say the reshaping temperature. Reshaping temperature is somewhere, you can say it ranges from 55 degrees to 75 based on the combination, based on the composition of the alloy. So let us take, we have commercially bought the material, that is shape memory wire, and that is like a manufacturer is already characterizing that and giving that this is the recrystallization temperature, that is 65. So that means 65 degrees Celsius is the recrystallization, I mean the recovery strain or recovery temperature for recovering the strain of it. Now I'm going to wind it, the wire. I'm just going to wind it. I'm going to play with it, right? So I'm going to wind it on my finger. Now it has taken a form of a spring. Now what happens? Like it is completely deformed, right? It's completely deformed, and I'm just telling, yeah, it is deformed. It's a normal wire, metallic wire. It is deformed. Now what I'm going to do is I'm going to subject this deformed wire into the warm water, which is of like 65 or 70 degrees Celsius. Warm water, or I'm just going to light it. So that means like lighter, I'm just going to inflate it. That means once it reaches to 75 degrees, 65 degrees Celsius, then it automatically comes back to the straight wire. So that means like it, how you're doing, even though if you're putting a knot onto it, it comes back. So that is what the shape memory effect. You can see that without the influence of any kind of mechanical loading, it can regain to its original shape. Now you'll understand in the next video, like how exactly this shape memory effect can be seen over here. So that's how the matter static state is the low temperature state, wherein we are going to deform it. Now we can see the shape memory effect. So there are generally two shape memory effects we can see. One is the one-way shape memory effect and two-way shape memory effect. What is this one-way shape memory effect? One-way shape memory effect, you can just clearly see in this picture that the rod or the wire is of straight line position, or you can say it's very straight horizontal position. Now, at the Martin static state, that is low temperature, normal room temperature, I'm going to bend it. That means I bend it. So it is bent now, right? Because this is a metallic element, it is plastically deformed. And once it is plastically deformed, what I'm going to do here? Now, this is the deformed position. After applying load, it is plastically deformed. And this is plastically deformed. Now, I'm going to subject this for the heated condition. That means I'm going to heat it. I'm going to heat this to 65 degrees Celsius or whatever the defined temperature is. So when I'm going to heat it to the defined temperature, then it regains back to the original shape. It regains back to the original shape. So, and when you are cooling this down, still it will be in the original position. So that is what the one-way shape memory effect is. I think this picture is self-explanatory. You can easily understand what this one-way shape memory effect is. So that is Martin-Sat is low temperature, alternating is high temperature. So that means we are heating this only to regain its back to the original shape. So that's what the one-way shape memory effect is. Now, just see here how this one-way shape memory effect can be shown. See, it is being deformed. We are going to light it. See. I think this is better explanatory. I think you can easily understand. And technically, if you are going to explain the same mechanism, then certainly we have a graph here. So in this graph, we can see the Martin-Sat, which has got in the atomic level, the twinning phenomenon can be seen over here. So what is twinning phenomenon is? Twinning phenomenon is the rearrangement of the atoms. So the crystalline material, this is the crystalline material, metallic element is a crystalline material, right? So in these crystalline materials, we can easily achieve the twinning phenomenon here under the influence of the thermal agitation and all. So now at the low temperature, now you can see this ordinate is showing the temperature, that is here the room temperature, here's the standing temperature level. Only we have to understand these two levels. One is the room temperature and one is alternating temperature. And here we have the loading phenomenon. That means the mechanical load. Now at this level, that is original level, what we're going to do is we are going to subject this under mechanical loading. At low temperature, of course, the room temperature, we are going to load it. And once it is loaded, it is deformed. It is deformed, and this deformed phenomenon can be again let this for the thermal agitation. We are going to heat it to 65 degrees or 75 degrees, whatever the strain recovery temperature, whatever is being defined, then that strain can be recovered at that temperature when we are heating. What is this? This is, let's take an example. Like I have a commercially available shape memory wire, which is having the recovery strain temperature of 60 degrees, 65 degrees Celsius. Now, this room temperature is 25 to 30 degrees Celsius, and I am just applying the load over here so that it can deform. It is deformed. Now, I am just going to subject this for 65 degrees Celsius. So that means I'm heating this to 65 degrees Celsius, and it has regained back to its original position. And again, this is the high temperature. That means I have heated this to 65 degrees Celsius. This is 65 degrees Celsius, and this is room temperature, that is 25 to 30 degrees Celsius. Now, again, when I am cooling this down, then again, it regains back to its original atomic structure. I mean, that is what the original structure I can get. That's how you can achieve it. Now, a two-way shape memory effect. I request participants to please turn off your mics. Okay. Now, two-way shape memory effect. What this two-way shape memory effect is? I'm sorry, I'm actually going a little slowly, thinking that so many are UG and PG level students. So that's why I'm just going a little slowly.
Yes, sir, you can continue, sir.
Researchers don't mind on this. Okay. So in two-way shape memory effect, it can memorize the two different shapes. Now, what I'm just saying is I have bent it into only one direction, right? And I'm just heating it and it's regaining back to its original shape. Now, it can memorize the two different shapes at two different temperature levels. So one is a low temperature level and another is high temperature level. So now we have to see what this two-way temperature is. So this two-way shape memory effect is, we can see in the Martel setting, that is the low temperature level. It will be originally into the straight line, or it's very straight condition. Now I'm going to do a severe deformation. I'm going to apply a load and I'm going to heat it. And then when I'm heating, then it's coming back to one position. So that means after training, this can be achieved. These two shapes, what we are getting, these two shapes can be achieved only after rigorous training on it. So that means we have to apply cycling of this. So that means we have to apply for 40 cycles, 50 cycles, 30 cycles, then we are going to achieve these two different shapes. One may be into the one form and one may be into the sagging, and hogging can also be achieved. So this is the two-way shape memory effect. Or we can say one is into the winded condition and another into just a hogging condition, just making a kind of bow kind of shape. So this can be achieved in two-way shape memory effect. Now let's understand deep into it for the beginners, that once I have deformed, it is into a Martel static level, that is low temperature level, that is room temperature level only, right? So it is deformed now. Now what I'm going to do is I'm going to heat it to the whatever the regulated temperature or strain recovery temperature is. What the strain recovery temperature? 65 degrees Celsius. Let us see. So when I'm heating this to 65 degrees Celsius, it has attained this temperature. Now what I'm doing, and I'm again cooling this down to the, let's say sub-room temperature, maybe at around 15 degrees Celsius or 10 degrees Celsius. So that is sub-room temperature. When I am cooling this down to sub-room temperature, then what happens? It has gained another shape. So these are at two temperature levels, that is high martensite and low martensite. It adopts the two different shapes on it. And then again, when I am heating it a second time, then it comes back to this particular shape. So that's how we can see in this video how exactly it gets the shape change. See, heating, cooling, heating, cooling. Now you can see this is getting one shape into the heated temperature, heated line, and then it has got another shape. So these two different shapes can be achieved in this way. Okay. Now you can say it's in form motor. You can see So this can also be achieved with the help of the shape memory stripe. Now you can see here, it is making two different shapes. So these two different shapes can help in making its movement. Dynamic can be achieved. A movement can be achieved over here. So this is how you can see here. Now we can just observe here once again. Like this is first shape, this second shape. First shape and second is this shape. And first shape, second shape. So these are the two different shapes that can be memorized. And again, when we are subjecting back to the 65 degrees Celsius, then it again straightens. That means it comes back to its original state. So that's how at two different cooling stages, it can memorize the two different shapes. So this is the two-way shape memory effect is. I think it's better explanatory. Now we're going to MR fluids. What is MR fluids? Magnetorheological fluids. Rheology is the study of change in viscosity, change in thickness of the fluids in general words, you can say. So this is how this rheology changes. Now we can say density can be changed. Of course, the arrangement can be changed, and with the influence of external stimulus, with the influence of external the addition of any materials, it changes its viscosity, density, specific gravity, everything, right? Now we are not going to add anything. We are not going to take out anything. This changes its viscosity. Generally, if you see, it is not changing its viscosity. It is making a mechanism in such a way that it acts that it has changed its viscosity. It has become a thick fluid or it has become a thin fluid, like that. Now, generally, in its normal state, when it is not magnetically agitated, when it is not under the influence of magnetic forces or magnetic flux, then certainly what it appears like just a liquid, black liquid. So here, the silicon oil is being suspended with the micro level or the soft ferromagnetic particles, soft ferromagnetic and iron particles, very soft particles of, let's say, of micron level, like 3 microns to 20 microns, 25 microns, of that range. So that particles. The softer the particle size or smaller the particle size is, you can say the better the magnetorheological effect can be achieved in that. So that means it can be better fitted in accordance with the magnetic fluxes. So now we can see under the influence of magnetic fluxes. So once it is magnetically agitated, then based on the magnetic flux, it makes a kind of wall between the two layers of the fluids. Like whatever the silicon oil you're using, what it makes is a wall between that. So based on the intensity of the magnetic flux, based on the strength of the magnetic flux, what it makes is it makes a stronger wall. So stronger wall means the fluid is suspended, the fluid or the liquid or the oil is suspended between the two walls of this particles, so ferromagnetic particles. So what it makes here, it makes a cushioning effect. That means the fluid cannot easily transmit it. It cannot easily move from one way to other way. So because these freely suspended ferromagnetic particles have arranged and has formed in accordance with the magnetic flux. Magnetic flux, what it's making. So it is making a kind of walls, and that's how it changes based on the intensity of the magnetism. It changes its cushioning effect. Now we can say when it is like it is designed for the high magnetic intensity, then you can say it offers very stiffer mechanism over there. When it is very stiffer, it can sustain a lot of larger loads. When it is like less intensity of the magnetism can be influenced, then certainly we can say it has given it can achieve the very cushioning effect over there. So that's how, based on the intensity of the magnetism, we can achieve the rheology or the change in viscosity, or the better or the appropriate cushioning effect can be achieved on it. So that's the mechanism of magnetorheological fluids. So that is why this MR fluids nowadays in sports cars, in aircraft dampers, and this landing gear dampers and all, we are being designed, are being developed with the help of this magnetorheological fluid, so that it can sustain, it can withstand the larger loads also, and it can be stable even in the normal or stationary loads as well. Now we can say the Boeing 787 is its takeoff and landing load is somewhere around 600 tons, 600 metric tons. So that That's too much, right? If we are having a mechanically designed dampers or suspension mechanism, then certainly we cannot sustain that. It cannot sustain onto the high impacts. It cannot sustain that. There may be the braking. If it breaks, then certainly it leads to crashing of the aircraft. Certainly, when it jumps, when you're talking about the sports cars, Formula cars, and all, so when it jumps or when it undergoes into the the roughy or very surface irregularities of the road, then it cannot withstand that. So that means it can easily be broken. So that's why we are going to design the dampers in such a way that in that dampers we are going to fill the MR fluids, which is again being attached with the rheostat and the magnetic the stimulator. So this magnetic stimulator is making based on the intensity or based on the deformation of whatever the deformation based on the surface irregularity it is being achieved, it enhances, it stops the resistance. So that's how the electrical conductance can be achieved. So with that electrical conductance, we know that magnetic field will be generated. So based on the electrical intensity, magnetic intensity can be achieved. And that magnetic intensity is directly being influenced onto this liquid, and that's how it's thickening the liquid in general. In general, it's thickening the liquid. So when we are coming to technical things, it is not thickening, it's just a mechanism of arranging of the ferromagnetic particles into a wall, into the layers, so that it can be highly stiffening. Stiffening effect can be achieved. So this is all the mechanism of stiffening of the ferromagnetic particles into the liquid. So that's how this mechanism can be achieved over here. So now the magnetic shape memory alloys. So we have understood the shape memory effect. So that is under the influence of the thermal agitation. That is what when the temperature is being changed, then we can achieve the shape memory effect there. So now this is the magnetic shape memory alloys. So these magnetic shape memory alloys are of the same principle. These alloys are also working on the same principle, but under the influence of magnetism. So these are not going to agitate it, and these are not going to change its shape from under the influence of changing temperatures, but under the influence of magnetic changes. So that is why these are called as magnetic shape memory alloys. Now, single crystalline, that is nickel, manganese, and gallium. So that's what these have got a different the alloying elements over here. So nickel and titanium was being used for normal SMA shape memory alloys. Now here for MSMA, we are going to use the gallium and manganese also. So these are having a different proportions and different alloying elements to achieve this thing. So now magnetic shape memory alloys are also being worked on the same principle. So we'll go to the next pH sensitive polymers. I think I'm going very slowly. I need to cover some trends and research opportunities as well. So pH sensitive polymers. So pH sensitive polymers are the polymers which are going to change its radical polymerization. Now we can say atomic transfer, radical polymerization, and reversible fragmentation chain transfer. So these can be achieved in this one, and pH sensitive polymers are going to the polymers which are going to respond onto the pH. That means under the influence of the chemical agitation. So that means when there is a chemical change, chemical agitation, maybe a kind of like toxicity, or maybe a kind of like the chemical influence, so it's going to swell. So that means the swelling phenomenon can be seen into the stripes of the pH sensitive polymers. So under the influence of chemical agitation, when it is being toxins are being added, when there is an acidic influence, then certainly it's going to change there. So that is what the same pH sensitive polymers are being used for the biological applications also, or the chemical applications as well. So that's what for chemical, that is wherever it is acidic influence, then it's going to change its shape. It's going to swell. And when it is being again removed off, then certainly it comes back to its original shape. So that's how the swelling phenomenon is going to describe that these are going to sense the acidic influence. See, now we can say the swallowing gel and collapse gel. So that's what we can say. Halochromic, and let's say I'm just going to cover this the chromogenic materials. So halochromic are the chemically influenced color changing elements. Now we can say sometimes you can see in the Pizza Hut and all the pizza delivery systems, you could see there is a sticker. So when it is like hot, the pizza or whatever you're getting, the home delivery, especially I've seen that in Canada and all. So that sticker is there. In that, sticker color changes. When it is cold, then sticker color changes. So that's what it is like. Halochromic, thermochromic stickers are being placed over there on the walls. So that means when it is hot, then only if it is like appeared in the red color, then only we have to buy. If it converts into a blue color, then we need not to buy, or it is like free to take out. So that means it is cold. So that is thermochromic sticker is being used. So in the same way, a halochromic is like it changes its color. It changes its color under the influence of the chemical agitation. So that's why it's like chromogenic elements under the influence of the thermal agitation. So it is called as the thermochromic, and then electrochromic are there. So that means it changes under the influence of electrical conduction. Now we can see an example, like why, where it is important, why we have to go for like chromogenic elements and all. Certainly, this class of elements are being used for the painting or surface, the surface treatments or the surface painting kind of applications. Now we can see in somewhere like powerhouses, or you can say the transmission units, you can say that there are more possibilities of electrical conductance because we are using the metallic elements only for casing and all. So there, it's like more common that it may be electrically conductive because of some accidents and all. Like we cannot see that, like whether the case is electrically conductive or not, whether the housing is electrically conductive or not. Then what we have to do is we have to just do some painting over there for the electrochromic painting could be done on some area. So when it is more prone for electrical conductance due to some accidents, then certainly in the high voltage areas, it will be very dangerous for the life, right? So what it changes its color under the influence of electrical conductance. So what it makes is on the housing of that particular machinery, what it happens when it is like electrically conducted, when there is a damage into our wires and all, then certainly it conducts, right? When it conducts, it changes its color. When it changes its color without going for any further inspection of to avoid the accidents, we can easily understand that it is conducted. And now we have to cut the mains, and then we have to see and do the corrective actions over there. So that's how we can understand without touching, without physically examining that. So we can just see and can understand that it is electrically conducted, and we can avoid the accidents and dangers. So like that, the examples can be taken up to the next level. So that's what the chromogenic and thermochromic, as I've told, it works on to the same level. So if you're understanding the construction development of these materials, it takes it will be this 1 hour will not be sufficient. So next we'll go for research opportunities and investigation gaps in smart materials. So what we need to do research in, and for the aspiring researchers, if they want to work for the smart materials, definitely it has got the future, because different applications could be explored under under the banner of the smart materials, structures, and intelligent class of materials and all. So these smart materials are most promising in different fields, as it's been said. So currently, we are using the smart shape memory alloys or shape memory based mechanisms into satellites, door opening and closing, and in aerospace in several applications we are using, naval applications we are using. Still, we can develop for the high functionality and for the high adaptability and high applicability. We can develop, we can characterize, we can do research and investigations onto these materials for the high applications in different areas of different industrial applications. Now, SMS can be used in flight dynamics for movement of flaps. Now we can see in airplanes, we will be having a linkage mechanism for the movement of the flaps, rudders, ailerons and all. So that makes a movement into the airplanes and all. Now we can avoid that mechanical linkages. We can prepare the wings that can be twisted, that can be changed its shape. The morphing capabilities can be achieved. Morphing of aircraft wings. The morphing capabilities can be achieved when we are using this shape memory based the reinforcement in the composite, so, and that can achieve a kind of the twisting mechanism, and the bending mechanism, buckling mechanism. So if we can achieve that, then certainly we need not to go for the conventional linkage mechanisms things. We can easily deploy this for the flight dynamics. We can use it for the high reliability. We can use it for the conduction as well. So that means it will be more sturdy, more stiff, and more reliable than the existing mechanisms. So that's what this investigations are still being used, and in UAVs and MAVs already is being deployed, and we have also done our research and we have published a patent in the Australian Australian patent organization about this morphing capabilities of the shape memory based composites, FRP composite. So this can be achieved in with the help of shape memory alloys. Automatic door opening and antenna expansion, antenna opening mechanism can be achieved. So for the solar panels of the satellites, it's already being used for the automatic door opening and closing for the expansion of the antennas and all. So we can still modify this. We can make still effective with the help of the solar radiations, and with the help of certain other physical stimulus. We can use it more functional and more steady mechanism can be achieved. So that means by characterizing, by developing the mechanism, and by repeated investigations to achieve the endurance of this particular mechanism, we can publish and we can do our research into this applications as well. Twisting in helicopter blades, as I've told, the same thing can be achieved even in the twisting of the helicopter blades. Now we can see the helicopter propellers are linked with so many linkages wherein we can achieve the forward movement, and angle of attack of the blades can be changed over there. So, right? So we can avoid with the help of this thing. So that means that when it is being influenced with the thermal agitator, when it is being used with the thermostats, then certainly it changes its shape, and angle of attack can also be changed for the upward movement. For the lift, for the drag, for the forward movement, and for the stationary conditions. Different mechanisms, different the flight dynamics can be controlled with just the change in the twisting angle of the propellers of the helicopter. Smart composite wings. So that's what the composite wings, as I told you, the morphing capabilities can be achieved just by embedding this shape memory stripes, shape memory wires into the fiber reinforced composite, so that we can achieve the different mechanisms the aircraft wings can achieve. The dynamics or the kinematics to it. So that can be used for the speed changing also, and that can be used for avoiding the turbulences as well. Turbulences, difference in change of the weather conditions, as well as for for achieving the flight dynamics as well. So these things can be achieved with just shape memory alloys application. So it has got its shape memory alloys are most promising because of it's easy access, and it's like easy in memorizing the shapes, and can be it can easily replace the mechanical components, multiple mechanical components with just a single structure. We can easily achieve that. Now into medical sciences, we can see the orthopedic implantations. The orthopedic implantations for the fractured bones or joining or hip replacement things, right? So now we can achieve this for the different, the change in the size of the bones and all. So when we are going to implant this, then certainly there will be a kind of like we can use, nowadays we are using the plates and clamps to join the broken, the broken bones. So if the elbow is being broken, or if the knee or the other bones are being broken, then certainly we are going to do a surgery there, and we are going to apply the plates, and we are just going to clamp so that it can fill the gap and it can rejoin. Now for rejoining, again after rejoining, what it happens when it regains, then there may be a kind of like strain, or there may be a kind of like stresses which are going to apply, or which are going to be applied both on the bone and as well as the plate, because of the changing shape. Now it is being filled, then certainly after being filled, then it applies over to that. So that means like when the mechanically deformed plates are there, then certainly it agitates the stresses both onto the mechanical elements as well and the tissues as well. I mean, you can say the bones as well. Now we have to understand that based on these things, like when the shape is being changed, then based on the body temperature, it can reshape. It can generate a stresses over there, and that stresses will make the broken or whatever the gap is there in between the bones. Then it can be like stressed to join it very faster, and can be more reliable than the normal metallic the joints or the plates. So that means under the influence of the body temperature itself, it can be stressed. That means like when it can apply the mechanical loading, then certainly what it makes, it generates a stress between the part A and part B of the bone, and that's how it can be like stressed, and it can be recovered and can fill the gap between the bones, and that's how the normal healing can be more quicker and faster. So that's what in orthopedic implantations also it can be having the better application. So we need to go for like compatibility of this. Of course, this titanium and nickel are the biocompatible, so we can use the nickel and titanium based alloys for the orthopedic and biomedical implantations as well. Composite structures with shape memory alloys embedded acts as a self-healing of the structures that avoids the catastrophic failures. As I've already told in the beginning of the session, that it can be used for the structural health monitoring and structural health healing purposes. So as I've told earlier, so that means if there is if I can see in detail, then if the aircraft is influenced or it comes under the turbulence heavy due to the weather changes and all, then what happens? These composites or FRP composites, as the wings and other parts of the aircraft is made up of the fiber reinforced composite, it may undergo the delamination, or there may be the crack generation into the structure. If crack is generated, then under the influence of the turbulence, then what it happens is like it is going to counter onto the structural health of that, and that is how the crack which is already generated starts propagating. And when cracks starts propagating, it leads to the catastrophic failures of the structure. So that means that leads to the accidents, that leads to the change in dynamics, flight dynamics, and that's how it can lead to the failure of the structure. And that structural failure can lead to a crash of the aircraft and all. So we can avoid this when we understand that shape memory alloys or shape memory alloys are embedded within the composites, and then it is being noted that once it is conducted, of course, these are the metallic elements, and nickel is again the conductor, good conductor, and it can be conducted, right? Electrically conduction is not going to affect on the shape of this. So when it is conducted, then certainly it can sense the change in shape of that. So that means when there is a crack is getting generated, then certainly it is being influenced with that crack. When it is being influenced with that crack, then certainly there will be a breakdown of electrical conductance. So when there is a breakdown of that electrical conductance, then we can easily understand that crack is started generating. Crack has generated. So with that understanding, what we can do is we can just agitate that particular area with the temperature. So that means when we are heating that, then it starts closing because stress concentration is more there. When it is stress concentration is more, it makes a kind of like reverse kind of like buckling phenomenon can be achieved in that. So this buckling phenomenon makes this to close the gap. So that means whatever the crack which is getting generated, we are going to apply the negative forces on that. When applying the compressive forces onto that, then the crack propagation can be avoided. So that is how in space we can avoid the catastrophic failures by stopping the crack propagation. So stopping the crack propagation can be achieved with just application of just changing in structure. So that means the structure itself can change its shape, and whatever the thing that is generated, that means crack when it is generating due to the acting stresses, so that can be closed by against its normal shape recovery. So that means the strain recovery can stop the catastrophic failures. So that's how we can achieve in that thing also as well. Under different weather conditions, we can assess and we can go for a different application. So that's what the structural health monitoring can also be done over there, and health healing can also be achieved with the help of shape memory alloys. Similarly, piezoelectric materials are there. That is PZT transducers are there, PVT are also there, and so many other combinations are there which are offering the different levels of the shape memory effects. So that's what it can be used for anti-icing mechanism. Now we can say, what is anti-icing? If the aircraft is flying at an altitude of 40,000 feet, so then certainly the temperature is minus 50 degrees Celsius there. And if it is like if it is flying, or if it is like landing or being accessed into areas, polar regions, then there the temperature is in negative scale. So this negative scale can lead to the easy deposition of moisture. So that means ice has got a tendency to accumulate and to make a kind of like slabbing kind of phenomenon can be achieved onto wings and to a dynamics of this aircrafts. Maybe the flaps, ruders, ailerons and all, it can be deposited over there. Once it is deposited, then there may be the difficulty in the normal motors to make the twisting or to the sliding of this ice. So that means there may be a first thing, that is moisture absorption of the structure. This moisture or the ice deposition onto the structure may leads to absorb the moisture or the water into the composites, because composites are highly it has got a tendency to absorb moisture easily. So once the moisture is being absorbed into the composites, that is aircraft structures, then certainly it delaminates, it fails, or you can say it loses its strength. So that is why this moisture and the icing is always dangerous for the aircraft structure. So we have to avoid this. So to do that, what we have to do, we have to achieve a mechanism of removing the ice, because it has got a tendency, the moisture or the ice has got a tendency to agglomerate or to join the molecules and make a kind of ice slabs onto this. Then it will be firstly depositing, or you can say it increases the weight. Second, it is like enhancing the moisture absorption tendency of the composites. And third thing is it avoids or it may jam onto the movement of the rudders and flaps. So that means in all these three ways, it will be having the negative effect on it. So that's why we have to do anti-icing. That means removal of the ice mechanism. We cannot use, since it's being aircraft structure is being influenced with so much of like drag forces and all, we cannot use any kind of like common linkage mechanisms over there. It's very difficult to use. So that's why what we are going to do is we are going to place this piezoelectric transducers into the composite on the upper layer of the composite, so that it can make a kind of bubbling effect. So when it is being influenced with the electrical current, then it makes a kind of like bubbling effect, very small bubbling effect. So how we can achieve this one? Bubbling effect is going to crack the ice. Once it is cracked, it can easily slide off the structure. So that can be achieved. This thing can be achieved with just a cracking of the ice layer. So once it is cracked, it can easily slide off. So that's how the bubbling effect can be achieved with the help of this piezoelectric transducers and all. So like that, we'll be having so many other mechanisms and applications, potential applications that can be explored in the further sessions and all. So MR and ER fluids, this is also having very good application areas which can be used for designing the high capacity dampers, which can be used for making a different, the high performance, the devices can be achieved with these things, right? To bridge the gaps and to make differently able to, what you can say, for the handicapped people, we can achieve a different sticks and all. So these are all there which are going to offer a high or optimum cushioning effect to vehicles for that can be designed for the differently able people and all. So many other applications are there that can be used for that, and like that, the color changing elements are also there that can be used for different coating things and all, especially nuclear plants and all. So we need to understand whether it is like the radioactive elements are being, there is any leakage into that, then we have to use that, because we cannot take the menace. I mean, we cannot take a risk of going and physically examining that. So that's why all we have to do is to understand whether there is any kind of leakage or any kind of change in electrical current, or whether there is a change in the chemical influence or also. So we can just understand into various industrial aspects of it. So we can investigate onto that, and then we can say the nano coating of structures to achieve the hydrophobic and those characteristics. Hydrophobic is very important. So it is already being coated into aircraft or to automobiles. Nowadays we can see The modern automobiles are equipped with hydrophobic coatings on that. So hydrophobic coating, that means like it will not allow the water particles or water droplets to deposit on top. It can easily slide off, just like a lotus leaf. So the nano coating can be, or the hydrophobic coating can be achieved with the help of, that can be also used. And then fire retardant polymers and structures. So this is also one of the areas which is more promising at all. So now nano-coated biocompatible alloys. So that means you can say if it is the knee replacement, hip replacement at all, then obviously there will be a kind of like the movement of the two different joints. Organizers, I'm extremely sorry that I have just extended to the level. I hope you don't mind if I'm extending to another 15 minutes. If you can allow me to speak for another 15 minutes, I can continue the session. Can I?
Yes, sir.
Hello?
Yes, sir. Sure, sir.
Yeah,
Sure, sir.
Yeah, thank you.
Yes,
Thank you.
sir.
I'm sorry. Since I knew that there are some student level students are also there, then so I have just gone into very deep into explanation onto fundamentals. So anyhow, so now we can use the nano-coated biocompatible alloys. Now what we are doing is we are going to use the nickel-coated carbon nanotubes, nanoclays and all to coat onto the contact surfaces. Now we can say we'll be having the two phases of this in knee replacement and all, so that the respective the kinetics can also be achieved in that, and also it should offer the optimum tribological properties as well, because one is cell body weight will be there. Second is since the surface contacts are being made, and though we are offering the fluids into it, there will be it's being influenced by the wear and all. So that's why to avoid that, it should be like tribologically feasible. So now we are going to do the nano coating onto it so that its life can be enhanced. So nickel is again biocompatible element, but we cannot use the carboxyl or or differently functionalized carbon nanotubes or the nanoclay to it, but we can use the nano electroplated or electroplated nanotubes can be used, that is nickel plated carbon nanotubes can be used for surface coating, so that it can enhance the tribological properties and it can totally enhance the life of the implant. So especially to the orthopedic replacement, orthopedic parts replacement, we can use this thing, and this can generally enhance the life of the implants to up to 15 years. Now generally nowadays we have for 7 to 10 years only. Now we can enhance with the influence of this electroplated CNTs coating, it can enhance to 15 years more. So that's what the general study is saying. So we can use this as a study for our continuous research as well. High performance and economical stents. As I've told, the stents which are going to use for for angioplasty. So that stents for the blockages of the heart vessels and all. So it can be we can develop the economically and highly biocompatible, bioadaptable stents with the help of shape memory alloys. So this is also one of the studies we can use onto the life of the stents and all. Now characterization of the smart materials and alloys. Generally, we have to determine this. So these are still the materials, and so many research gaps are there, investigation gaps are there for this smart materials. So we have to characterize, we have to understand the behavior under the influence, influence of a different intensity, different magnitude of the physical stimulus. So we have to go for the carefully monitoring, carefully understanding under the influence of different compositions, under the influence of a different magnitude and intensity of the physical stimulus, how it is going to react, how it is going to give optimum solutions or the better effect of smart characteristics can be achieved in that. So to understand that, we have to understand first the material. We have to characterize it in different aspects. So characterizing it can be achieved with different analytical ways or different micro structural analysis and all. So to characterize it, we can go for different electron microscopes. We can use scanning electron microscopes. We can use transmission electron microscopes, or scanning probe microscopes, or atomic force microscopes to understand the better surface characteristics and all. And then we can understand its crystallography, its crystalline structure, its atomic influence, its electron influence. Everything can be achieved with different analysis or different spectrums that can be achieved with X-ray diffraction spectroscopy, Fourier transforms, infrared spectroscopy, FTIR, XRD, FTIR, or scanning calorimetric spectroscopy, that is digital differential scanning calorimetry, that is DSM, and different other are there. So to understand the influence of the different physical stimulus onto the characteristics of that particular material. So we can, the characterization itself is a very complicated and highly sophisticated areas wherein we can investigate a small class of alloy or the material, and we can investigate onto different characteristics of it. So to understand the fractographic, to understand the not only the mechanical means, but onto a different means as well. Right? That's thermodynamics of the materials and other characteristics. That's how it is being influenced with the the chemical aggregations, or you can say the different compositions, or it makes a different crystallography or crystalline structures is going to be affected onto different mechanical, thermal, electrical properties. So we can very carefully understand. So one of the best things that we are doing is the EBSD, electron backscattered diffraction of the SEM. SEM, it has got EBSD is there. In EBSD, we can clearly understand like how many compositions are being used, how many different materials are being used in a different color contours and all. So EBSD you might have seen with an attachment with the scanning electron microscope, so which is going to give a categorization of the different materials which are being used in the different patches. So that's how the atomic influence is being made into the boundaries, grain boundaries of that. So to understand that, we are going to use the energy dispersive spectroscopy. So that is another attachment with the SEM. So which is going to give a spectroscopic, which is quite similar graphs which are going to be offered like a XRD, X-ray diffraction. So that we can understand the crystallography, atomic influence, and type of like the crystals we have, and how exactly these materials are being the influence with different atomic arrangements and all. And now this EBSD can be seen for better understanding of the topographies and morphologies. We can use the three-dimensional EBSD graphs. So that's what the with the help of FIB, focused ion beam milling, we can just mill the surface. Since we know that SEM can give only the surface characteristics of it, only one surface image can be given. So that's why we can just mill one surface with the help of focused ion beam milling, and we can take another layer. So like that, 30 to 40 layers, we are going to do scanning and milling, scanning and milling, scanning and milling. So after that, we are going to achieve the three-dimensional graph of it. So that can be seen. So this is a two-dimensional graph. Only the single surface graph can be achieved here. So hafnium and aluminum are the two different elements which were being used. And the patches of the hafnium can be seen over here in the boundaries over here. Now you can see aluminum can be seen in here dark colors, and hafnium, which is having the 72 atomic number. Hafnium has got a 72 atomic number, whereas aluminum has got 13. So that's how it is making a different the close patches over here. So that shows how exactly the hafnium is making its the grain formations, and how aluminum is being taken up over here. So now only the one surface can be seen over here. Now with the help of FIB, that is focused ion beam milling, we can achieve the three-dimensional graphs with the different intensities over here. Now let me just focus onto this three-dimensional graph. Now we can synthesize the three-dimensional graph with the help of different layers. Now we can see 30 to 40 layers of milling we are doing. We are just scanning one surface, and up to 100 nanometers we are milling, and we are taking another scan of that. And again we are milling and taking another scan of that. So that means we are building this with with the with the help of this focused dynamic mechanics, so that we can generate the three-dimensional graphs which can show how exactly the deposition of the different elements can be seen over here. To understand the metallic based the smart materials or any kind of metallic or intermetallic elements to be deployed into to form the alloys, then that can easily be monitored, that can easily be studied, and different physical properties can be studied with the help of this three-dimensional EBSD graphs and all. Now, research trends in smart materials. I think I need to skip this thing, and now I'm going to just show some research, the published and unpublished data on this. Now, buckling phenomenon has been achieved in this. Now we can see, just a minute. I'm sorry, I think I've just gone back. Now we can see here the composite layer is formed over here. In this composite layers, now we can see very clearly see here the composites is made with the different layers over here. Now, polycrystalline fiber is used over here, and the graphene fiber is also used. Graphite fiber is also used, and the shape memory alloy is also used. So, in the different tracks, we are investigating the buckling phenomenon here. So that means the shape memory alloy is trained with different cyclings. So with that different cyclings, it is being trained to buckle. So now we can see the efficiency of this buckling, and we can see the curvatures it has achieved in R1 and R2, R3. Are three curvatures we have achieved over here. Now, in these different stacks, now we can see it's only a UX, wherein only, now we can say only SMA is being used. And here it has got a different stacking of the PCF, PGF, and SMA into different stacking sequences we have used here. And in different stacking sequences, it has performed onto the resistance, because the material itself has got the stiffness against the moment. So that means the buckling phenomenon cannot be easily achieved here because it has got the different stiffnesses. So the matrix material what we have used here, so that is it has got its own stiffness. The fiber which we have used here, so that has got its own stiffness, and the composite itself has got its own stiffness that resists the easy buckling of the materials. Though we are training, though we are agitating thermally, it has got its own limitations. So that's what in this study we have seen, that it has got the buckling phenomenon has achieved over here. Now, in different cycling, we can see here at different temperature levels, we have seen the elasticity modulus has got varied over here, and after 90 degrees, it has got a kind of like steady state has been achieved in the elasticity modulus. Now we can see here it has been varied from 80 to 90 of MPa. We can see in that particular compositions. Now you can see the recovery speed, the recovery stresses has been seen over here for the 3%, 4%, and 5%. We can see here under the influence of the different, that's room temperature to the 160, 170 degrees Celsius. Now we can see over here. So these are all the unpublished data. So that's why I'm just like not explaining more onto this. So these are the investigations that already we have, we have taken up. Now it has to be published. In different, cycling, it has performed, it has given a different stiffness and different buckling phenomenon. It has proved. So that's how, with the influence of the shape memory wires, which is being embedded into the fiber reinforced composites to give the better buckling effects onto that. So this better buckling effects can be used for, avoiding the crack propagations. It can be used for attaining the shape changes of the aircraft structures or any automotive structures and all. So that can be used with the embedment of the shape memory alloy wires. So the commercially available nitinols we have used, that's nickel titanium based alloys we have used, so which are giving the better shape memory effect. Now we can see the mechanism here. We have used the 3 wires into this wire, and we have placed this into the most bottom way, so that it can give a better buckling effect onto it. Now the 2 millimeter thick stripe we have used, or specimen we have used, and we have, before embedment, we have gone with different cycling of training, cycles of training. So that means we have trained this to, to memorize the shape in different cycling, and it has proved that it has given the optimum cycling. Now we can say the red color shows it has given the high stress carrying capacity. That's what the high recovery stresses can be achieved over here in the 10 cycles, and the lowest we have achieved into the 25 cycles. So that's what we have just optimized the cycling of the training. So that means we have achieved in this one by different cycling, cycles of training, that 5 cycles, 10 cycles for training to memorize the shape memory effect. So that's what the different volume fractions of the shape memory alloy wires we have used here. With 3 to 8 we have used here, and different volume fractions starting from 4% to the 12% we have reinforced with the shape memory wires to achieve a different buckling effects and different level of deformations we have achieved over there. And 750 is the recrystallization temperature, that is original recrystallization temperature of the SMA wires we have used here. Original recrystallization means when we are heating this to 750 degrees Celsius, then it will remember that particular shape at that temperature. That means 750 degrees Celsius, if we are influencing, if we are heating to 750 degrees Celsius, then it is going to forget. That is the amnesia state. Amnesia state means it is forgetting all the shapes which is previously trained and all. And now it is going to remember, it is going to take as the base shape at that particular temperature, at that particular instance. So then after we can memorize and we can train the material to remember a particular shape with different training sessions. So that's how these are the things we can see here. The 1, 3, and 8 shape memory wires we have used here, and we are going to understand the buckling phenomena with the mounting of the strain gauge and all. Now the placement of the shape memory wires you can see here, and the neutral axis also you can see here in the thickness. So this is how the research is going on in our research center. Now this is also gives you a different temperature levels. It gives you the stress strain curves starting from 30 degrees Celsius, that is room temperature, to the 80 degrees Celsius. So that's what we have characterized, and we have though we have obtained from the commercially available SMA, we have trained this and we have tried to achieve how it is going to be benefited into a structural health or structural strength. So this only shape memory wires are giving so and so the stresses here we can see at different temperatures. So this characterization and the moduli of the investigations is being shown out here. So that completes the session. For further queries, anybody can contact me on the aforementioned the contact. So this is all our thing. Thank you so much, and I appreciate if anybody raise questions related to the session. Questions can be asked. I welcome the questions. Hello, am I audible?
Yes, sir, you are audible.
Yeah. So questions are welcome. If any queries are there pertaining, or you can ask me queries onto my aforementioned email ID as well. So I'll write my email ID.
Any questions participant can ask.
Good afternoon, sir. My name is Azim Pasha. Sir, can these smart materials can be used for today's energy crisis? Can it will be act as an active member in reducing energy crisis?
Pardon me, I could not get your question. Can you please repeat again? In energy crisis, smart materials can be used?
Smart materials can be plays an active role in reducing the energy crisis. Can be acts as a sustainable material?
Yeah, actually the thing is, like as I have told, smart materials are the class of material, it's not only the shape memory alloys or any particular form. In energy crisis, it's completely different. Now we can see that when it undergoes to the cryogenic level, now we can say the nickel can be used in the the negative temperatures. When it goes to -50 to -100, then it acts as a superconductor. For that, it is it can be used only in the space applications. For now, I can say, or to the places wherein we can constrain these temperature levels to in a very confinement. But in energy crisis, like in the general applications, in the transmission of energy and all, I don't think it will be more effective, because we cannot achieve such a constrained environment, such a confinement we cannot achieve, and we cannot maintain that thing, right, in the transmission of energy and all. But it can definitely be used as superconductors into the satellites and space applications, where generally the temperature is very, very less. So it goes, if it is being used into the satellites, satellites which is being used for the surveillance into the Mars and Jupiter and all, there the temperature is -50 to -70 degrees Celsius. And as the temperature goes down, the molecules and the electrons will be very quicker, and that's how this can be used. This nickel and titanium based alloys, with what we're using, the nickel based especially, nickel is again the very good conductor. So that's how this can be act as a superconductor, and that's where we can use this as to counter this energy losses, we can say. For energy crisis, no, I don't think it can be used over here, because we cannot achieve that cryogenic temperature levels on this. But in the cryogenic temperature levels, we can definitely we can use this as a superconductor, wherein the losses can be nullified. Nowadays, we have got a 30 to 70% of losses we can see in the energy transmission itself. So based on that, we can say, hope the answer is done.
Sir, what about the cost and lifespan of smart material over conventionally used materials, sir?
Yes, definitely. When it comes to the costing, certainly these are the advanced materials. So still it is into the research and investigation level. So now if you are going to buy the commercially available shape and alloys, it will be costing too much. Now we can say like the SMA wire, which is of like 0.5 mm to 1 mm, it will cost 1,500 to 5,000 also for just 1 meter of wire. So that means it's based on the type of like characterization these people have done and investigation they have done and development what they're doing. It varies. So it's very expensive for now, but that is why we are encouraging the research and investigations and development of these smart materials in whatever the beat. So if we are investigating and developing the highly functional and highly adaptable material, then certainly the cost can be reduced. Definitely it can be reduced. So currently it is very expensive. It cannot be used for the conventional applications and all. It can be used for the highly sensitive applications, and that's how it is encouraging a lot of research and investigations into these areas.
Okay, thank you, sir. Thank you, sir.
So further questions can be entertained through email also, and people who are interested in acquiring more knowledge into this area and arena and to be a part of these investigations can contact me on my email ID, which is already given. Thank you so much. Thanks for organizing the session. Thank you, Mr. Azim Pasha. And
thank
you so much, sir. Yeah.
Yes, sir. Thank you so much, sir. And now I request our Dr. Sumud Daniel, sir, HOD Department of Mechanical Engineering, to give vote of.
Thank you, Harish. Thank you, sir. Thank you, Dr. Syed Basith Muzammil, sir. The session was informative. Thank you once again, sir, for accepting our invitation to hold session in Vrindavan College of Engineering, sir.
Yeah.
And I thank
being the part of this organization, sir. And actually, Dr. Naim was very much cordial, and he was very close friend of mine. And it's like it's really heart-pinching news to hear that he's left us for the heavenly abode. So we pray for his the heavenly abode on this, and may his soul be rest in peace. And certainly, I was the part of the Brindavan institution, and I will remain the part of this for the social causes and the conveyance of the knowledge, and be a part of any kind of like R&D activities, which may be further taken up into future course of actions.
Thank you, sir. I thank our beloved chairman and respected principal for their wholehearted support for organizing this webinar. I thank all HODs and faculties and professors of other colleges for attending this webinar. I thank our coordinators and all faculties who made this webinar successful. And also I thank our students who had the patience to listen for the informative session held by our Dr. Syed Basith Muzammil, sir. Thank you, sir. Thank you once again for all the participants and faculties and respected HODs and my dear students. Thank you, sir.
Thank you so much, sir. Shall we conclude the session, sir?
Yes,
Yeah.
sir.
Thank you.
Okay, so thank you one and all for participating in this webinar.
Yes, sir.
Now we'll conclude this one.